Okay, so does anybody have any questions on the stuff that's, I haven't got to your stoplight homeworks yet. I will do that probably early next week, so either Tuesday or Thursday you'll have them.
About problem 3.
Problem 3? Okay, yeah, that's on my list to go over, so we'll do that. Any others? Okay, so a couple, let me put the screen up for a second, a couple of little details that I saw, and it didn't mark off for this kind of stuff, but on a lot of your papers I wrote it on, just so it'd be there, you would know. When you're writing a hex number, like in problem 1, you generally notate somehow that it's a hex number. So just writing, 67 doesn't mean, we would normally assume that that's base 10, and we had all those representations in class, how we normally do that. So you could have 67 base 16, or the one that I wrote is 0x 67. That's a pretty common way to write it. That's how you generally see it in code that people have written as well. Likewise, for binary, you don't have to separate. So you can write 00011100 like that. Or you can, as we showed, put an underscore in there to separate it into nibbles of 4 bits. That just makes it a little easier to look at when you're trying to figure out what's going on. There were a couple people that did traditional commas every 3 characters and don't do that. There's nothing that technically says you can't, but we don't think of groups of binary numbers in 3 bits. We only think in 4. Okay, so group into 4s. On the 256 decimal in the first problem, I didn't specify, and I changed this on the website to specify this now, so that the next time we use this assignment, we won't have this problem. This is my fault, so nobody got counted off for it. But a lot of people wrote 1,000,000, which is right. That is 256 in binary. But let's say we only had an 8-bit processor, an 8-bit variable. What's going to happen is that 1 goes away because your processor is only storing 8 bits. And now 256, you're back to 0 again. And you just start counting up again. So that's called counter rollover. You can think of it kind of like when your odometer rolls over in your car, though none of them are going to now. They're all 6-digit odometers. But that can be a problem, and this strikes a lot of hardware in the field. For example, the Boeing Dreamliner, one of their new airplanes, it has to be rebooted every month, or it could potentially fall out of the sky, because after 40-something days, there is a counter rollover issue in the flight computer that makes it lock up.
What is this?
The Boeing Dreamliner.
Yeah.
Yeah. It's not running Windows, I don't think. But this happens. You'll see issues where there's a Swedish rail system where they had this setup that would count the number of axles as a train went by, and it would radio that back so the conductor would be sure they haven't lost a car somewhere, that there's not a problem on the train. And now that we're making longer and longer trains, they ran into an issue of it would start reporting that they had 10 cars or something because it stored it in an 8-bit register, and now they had 266 cars or something like that, and there was a counter rollover issue there. So if you see stuff that's happening in your projects, this could happen on your Arduino. I've seen it in some firmware systems that I've done as well. Right, after a certain number of seconds, something always happens. Look for counter rollover. This will get you. On a processor that I commonly use, it's like 53 point something seconds is the counter rollover period. And so if I mess up, I see these weird 53-second cycle glitches. So that was the point of that problem, was to show you that counter rollover exists. But everybody was technically right by adding a 9th bit. We just don't have 9-bit processors, so you'd have to go up to a 12 or 18-bit representation. Okay, I think everybody got number 2 just fine. Number 3, and I didn't count off much on this because if you had some kind of explanation of why your answer was right, you thought, then there's some partial credit anyway. What 2 values in the table would be easy to use as troubleshooting characters when looking at the signal on an oscilloscope or a logic analyzer? What I was looking for, that works well, was AA and 55. So if you look at their binary representation. So if you're looking at an oscilloscope or a logic analyzer, you're seeing a time series of ones and zeros. AA is 10, 10, 10, 10, and 55 is 01, 01, 01, 01. So you would just see a square wave with a 50% duty cycle. So that would be 1, the other one would be the complement of it. And you can do logic operations and do things like and or those together and get very nice all zeros or all ones, right? So some people said, like 0x FF and 0x 00. And here you have no idea. If you look at an oscilloscope screen for 0x FF, it's going to be like that, and for 0x 00, it's going to be like that. And you have no idea if anything's happening at all. Is your processor even running? Because you just see a flat line. So it's not very diagnostic. Does that make sense to those that missed it?
So how does that help troubleshooting?
So you can say, send the character 0x AA or 0x 55, and you would see this on the oscilloscope or on the logic analyzer. You would see this square wave. And that's pretty easy to notice, this nice 50% duty cycle square wave on a screen. Whereas if, say we picked some random, let's go over here. Let's say that we picked some random number or whatever our processor was putting out that looked like this. Well, if you see it on the oscilloscope screen, it's going to be 0, 1, 1, 0, 0, 0, 1, 1. And that's maybe hard to tell. What's the duty cycle? Are there 2 ones there? How many zeros are there? So seeing a nice 50% alternating waves, easy to do.
So is the oscilloscope all 8-bit or they have 32-bit versions?
So oscilloscope, you're seeing voltage across time. You're seeing a graph of voltage and time. It's an analog tool. Yeah. People feel okay about that now? Okay. And number 7, which, like I said, again, I didn't count much off of anybody on this, as long as you had something down. And I rewrote the question and actually broke it into 2 questions for the future. So thanks for helping debug this, and that's why nobody got a lot counted off. A few things that I had in mind when I wrote the question would be things like multiply floating point numbers so that they're integers for the part that you care about. Like we talked about, if you had a temperature of 25.6, well, you could multiply it by 10, so you have the number 256, and you can do just integer operations on that. That would be one way. You can use, there is a floating point library, though I don't recommend it unless you really need it. So you could use libraries. Some people wrote that. You could do some binary math. Another big one that we mentioned was lookup tables. So for sine or logarithm or cosine or things that might not be in your processor as math functions, there might be a lookup table that you could use. And those are just a few examples, but that's kind of let you know what I was looking for there. So any other questions about the binary homework? No? Okay, if you turned in a drawing, mechanical drawing, you got 10 points out of 10. I put a couple of comments on the sticky note that's with yours. Some of them it was pretty hard to find things to comment on because you all did a really good job overall. So if you have any questions about any of the comments, let me know, or if you can't read them, because that's a very real possibility with my handwriting. Okay, so everybody good with digital representation, mechanical drawing, things that we've talked about the last few classes? Has anybody played with Onshape more? A couple people? Yeah. Really, I encourage you to go watch those videos on their website, the Getting Started series. It'll take you like 45 minutes to do, but it'll make you way faster and more productive. I was talking to someone this morning about you can design multiple parts and put them together into assemblies, so you can build your whole machine virtually. They show you how to do that in those videos, but we didn't have time to do it in class. So if people have a lot of problems with it, let me know, and we can always do another in-class session on it. Sound good? Okay. So today, we talked about how to draw things and how to make them in CAD, but we haven't really talked about some of the fundamentals of mechanical design. And to let you know, I'm going to cover about 6 engineering courses in 45 minutes or so. So there's 0 depth on a lot of this. It's to let you know that it's there, and you should go learn this and look it up when you need to. And if I leave out something that one of you knows and thinks is important, let me know, and we'll discuss it. So we've talked about software design patterns before, and in mechanical engineering, well, in all of engineering, there's something very similar. We use these well-tested patterns of designing and doing things. You need to move something, you need to translate it in one axis. Okay, here's 3 or 4 ways that we know how to do that. They work well. We've used them in devices for 50, 100 years, and we know where the failure points are. We know what their advantages and disadvantages are. So we'll look at some of those sort of mechanical design patterns, and for example, using bearings to support things that need to rotate and have low friction and low wear. And we'll talk about those, for example. Anything that you design is going to have to deal with all of these things. There's going to be bending and twisting involved, some kind of bending of a beam or torsion on the beam. There's going to be internal pressure possibly, especially if it's a lab device, and external pressure, even if it's just atmospheric pressure. If it moves, it's going to vibrate in some way, shape, or form, and we generally want to minimize that unless its purpose is to vibrate, in which case you need to do very careful design. And then it's also going to have to deal with static and dynamic loads. So a static load is, this building has to support itself. That's a load that's there all the time. Again, that's a whole class in engineering. Dynamic loads, that's another whole class in engineering, where you've got loads that are dynamic loads that change. So bending and twisting are, I'm going to say, relatively simple to calculate. For complex geometries, you have to use modeling tools. For example, you can integrate a finite element modeling tool with Onshape. And if you design this complicated part, you can simulate, okay, I'm going to load this up with so many newtons. And it will tell you exactly what the bend would be, where the stress concentrations would be. It's pretty nice. But for simple geometries, which a lot of what we're going to design for the lab is, there are analytical formulas that we can use. I'm not going to put a bunch of analytical formulas up here because we don't need to see the formulas and look at the terms all together. Everybody should be pretty comfortable doing them. I think the most complicated thing in them is a line integral, so it should be set there. But the idea is try to simplify the system as much as you can. Maybe consider it just a beam that's fixed at one end and you're loading it, and calculate how much deflection you're going to get. Is that acceptable? Is there going to be too much strain? Are you going to go into an inelastic realm? And so, for example, on this beam, you can see here's an in shot, so it's a rectangular beam. And as it's bending on the top here, we have tensile stresses, and here we have compressive stresses. There will be some formulas. You can get this book, Building Scientific Apparatus, that you had to read the first chapter of for the first week of the class. You can get it online from the library, and they have all of the analytical formulas for the simple geometries in there. You can find them online too. So internal pressure is something that a lot of us deal with. I would say almost everybody possibly. When you're doing rock mechanics or just laboratory experiments where you've got some kind of a pressure cell and you've got your material in there and you're using gas or oil or something to confine it or to exert pressure on it. This is a common geochemical reactor from PAR Instrument Company. So these are used for a lot of things like gas hydrate studies, where you can put a fluid in here and put a high pressure gas in and then refrigerate the whole thing or heat the whole thing up. And they are surprisingly expensive. This pressure vessel is probably about this tall and would probably cost you about $5,000 for just the vessel, not the top and the threads and all that. So they aren't cheap, and we'll talk about pressure vessels some more next week. But dealing with internal pressures is really important, because something like this, if it were to fail because you designed too thin of a wall or too weak of a seal on the cap, could potentially be very damaging to the lab and potentially be lethal if it's something huge at a very high pressure. External pressures seem like the same story because you just have pressure, but except now the pressure's on the outside of the vessel. This would be something that would house subsea electronics. So you would put your circuit boards in there for whatever that goes on the outside of a submersible to do some study, let's say, and submerge it. So you want to keep all the electronics dry, but have some connections to them. Now the pressure's on the outside, you have atmospheric pressure on the inside possibly. And there's a lot of different design considerations you have to use for internal versus external pressure, believe it or not. Another common practice with these is you can, if the equipment inside can take some pressure, but not the pressure that you're going to be at depth. Let's say you're at 250 meters water depth, which is 400-ish PSI, then you could fill this with oil and have oil support part of the load from the water. So the vessel wouldn't have to be quite as strong. But then whatever's in the oil needs to be able to support part of the load as well. Make sense? You'll also often see pressure vessels having domed ends. I don't think we're going to have time to go into any of that in terms of design. It's incredibly complicated. So we're going to stick with cylindrical vessels with flat end plates on them. This is another sealing mechanism. I just find fascinating that this even works. It shows you that you should consider all kinds of materials. This is the guts of an ocean bottom seismometer up at Woods Hole. And so they've got all kinds of logger electronics and all this stuff in here. There's a battery down there. What it is encased in, and these go down to thousands of meters depth, that is a solid glass sphere, just like windshield glass. But it's very thick, it's precision ground, and then these two precision ground glass surfaces mate together and they clamp it. And that's good to thousands of meters of water depth. It's pretty incredible. The catch is, if there is any hairline fracture, we all know what happens to small fractures. They'll eventually grow pretty quick. And occasionally, they do get some of these that might have a slight scratch that they didn't notice. And 8 or 10 months into the deployment beneath the sea, it goes, and that's about, many tens of thousands of dollars. It just implodes. But I would never have thought of trying to make this out of glass. My first instinct would have been to go to a titanium sphere, but they chose glass, and it's worked pretty well for them. And vibration, this is the most classical example of vibration and or dynamic loading, but mostly vibration on a structure. This is the Tacoma Narrows Bridge, and in the wind, it would start twisting like crazy. It naturally resonated there, and eventually it was destroyed. If you look at modern bridge designs now, you'll see they don't have this solid side. They have sides that are open and vented to allow the wind to pass through more easily. And they're also designed so that they don't resonate at this dangerous frequency. So vibration can do this to a bridge. It can also do this to machines. If you have something that's rotating rapidly, say a pump rotor or anything like that, that's a little bit out of balance and it's vibrating, it's going to wear the seals out, it's going to wear the bearings out, and it could cause catastrophic failure at some point. When you also have things moving in fluids like propellers, you can even get cavitation, where you get bubbles that form on the surface, and they can eat away at the propeller and eventually cause it to fail. So if you're dealing with things moving in fluids or rapidly rotating things, vibration is a big concern. But now that we've covered each of those slides being a class into itself in engineering, that you're aware of them anyway, talk about how we describe how a mechanism works, how many degrees of freedom it has. So there are 6 fundamental degrees of freedom. So say I've got my slide clicker here. I can move it forward and backward, side to side, up and down. We're all familiar with those. So that's 3. But I can also twist it along this axis, or this axis. So those are the 6 degrees of freedom. It's like if you can imagine an airplane that can translate in any direction. It can bank, it can yaw, and it can pitch. So we can describe the position and the orientation of an object completely with these 6 numbers. So I'm going to show you a couple of simple mechanical designs. When you're designing things, you often say, I want to constrain this to have 1 degree of freedom or 2 degrees of freedom. You don't want it to be able to move anywhere at once, or you probably wouldn't be building this frame in this machine. So let's look at this assembly. It's two metal bars, let's say, with a pin between them there so that they can rotate. So how many degrees of freedom would this system have? Yeah, it's just got 1 degree of freedom, so it can just bend. It can't go like this. The pieces can't move apart. They can't move like this. It can just rotate about that axis. But it's a rotation. It's not a translation of the whole thing, right? So it's just this rotation, this delta theta about that pivot point.
But so So for the 6 degrees of freedom, it's 3 translation, 3 rotation.
Right.
So, I guess, because that can obviously put in 3 degrees of translation, you're just not showing.
Okay, yeah, fair. The parts, you can move the whole assembly, but these parts can't move in those 3 degrees, right? So, that makes sense? Okay, let's do another one. This one, let's say a 3-legged stool. If you have tables like these that have 4 legs, they're actually over-constrained, technically, in an engineer's mind. That 4th leg's kind of useless, except that it's not in practicality. But let's say that this stool is constrained so that the legs are always touching the floor. We're sitting on it. So how many degrees of freedom does the 3-legged stool have?
0.
Can you not move? No, it's just a rigid stool. So it can translate in how many directions? If we're sitting on it?
Oh, if we're sitting on
So we're constrained to the legs are always touching the floor.
it, 2.
Yeah, so it can translate in 2. What about rotation? Can it rotate in any?
You can translate, rotate 1.
You can rotate in 1. So it's got 3 degrees of freedom total. You can translate side to side, forward and backward. And you can rotate like this, but if you rotate any other direction, it's a bad day because you're on the floor. All right, I think there's just one more here. This is one of those little, you could think of like a flag holder or something. You could mount it on the side of your house and put the flag in there and position it. So how many degrees of freedom does this have? And it's kind of tricky.
5, 4,
Right direction. So 3 degrees of freedom. So this pivot can rotate this way, it can rotate in this way, and it can twist, but it's not actually translating anywhere. It's still bolted to the same place on the side of your house. Right? So here's the pivot sticking up. I can go like this, I can go like this, I can go like this, but that's it. So just 3 degrees of freedom in that system. And something important to consider when you're doing your design, especially for your projects, is how many degrees of freedom does your system need to have, and how many are you constraining? Otherwise, you might have something that can flop around or move in places you don't intend it to. And the last thing you want is to say, okay, well, to use this, you have to hold this here and wait. Okay, put some pressure on it, and then let go, because you don't have the design well constrained. Oh, I lied. I think there's one more. This one is a pin and slot mechanism. This is pretty common. So we've got a bar with a slot in it here. This pin rides in that slot so that this bar can move up and down and twist on the pin. So how many degrees of freedom does this have? Yep, it's just got 2 degrees of freedom. And that's a pretty common mechanical assembly that we see. So there are a few ways that we can constrain motion. One would be by V-grooving. So if you look at the bed of a lathe, like we saw over at the shop, you would see that they're called the ways of the lathe, these inverted V in this case, where the carriage travels along. So that constrains the carriage. It can't move side to side. It can't move up and down. It's clamped, really. So it can just move in one direction. One way that you can do this, and this is called kinematic design, that you can do this would be, let's say we've got a V-groove in a piece of metal, and we put a ball bearing here on this bottom of this plate. So we're constraining this plate, top view and side view, to move only in this direction, only one dimension of motion. It can't twist, and you could lift it, but you probably wouldn't want to, right? And then this is just a support out here. So are there any problems potentially with the drawing down there on the lower left? Anything that you see that you think could be improved upon? So V-grooves might not necessarily be the easiest thing to machine. Yeah, you can tilt the head of the lathe or the mill over and run it. But they are going to wear, because if you're using a ball bearing, the ball bearing is hardened steel. It's a lot harder than the material the V-groove's in, possibly. So it's going to wear. It's going to be more expensive to machine, and you're probably going to have to do some lapping and things to get the V-groove to be smooth enough. So there's a quick and dirty trick to get around this, which is you can get this hardened centerless steel shaft from McMaster, or any metal supply place. Just a long metal dowel rod that's hardened. It's as hard as that ball bearing. You just have the machine shop run their end mill down here. You put 2 pieces of this hardened rod in there, and now the ball bearing rides on those. So 2 things of equal hardness. You lubricate it, it's cheaper to machine, and it's going to be just fine. So it's still constraining to 1 degree of freedom, but cheaper. You can combine multiple dimensions of this. So let's say we had some kind of sample holder up here, and we needed it to be precisely positioned in the same way every time. We could have a plate done with V-grooves or with U-grooves and those bars. And in this case, every time you set the plate down on here, it's going to be in the same spot. It's constrained in translation and rotation, right? So there's no degrees of freedom once this plate is down. So, make sense? Okay. So bearings. There's a lot in here on bearings because they're really important for a lot of the things that we do. They're how we support moving parts and reduce the friction between them and reduce the wear between them. And there's a lot of different kinds of bearings. Not even all of them are shown here. And they come in all sizes, you know, from tiny bearings, to bearings that are, you know, as tall as I am, that might go on a ship's propeller or something like that. They're huge. And if you Google large bearings and image search it, you'll see some mind-blowing things. We'll talk about some of the types, but just to point out, you can see there's some that are tapered. So they've got these rollers, and they're not straight. They're tapered on the sides. Here are some that are mounted in, these are called pillow blocks, that you can mount down to your base plate for your apparatus. These have these cylindrical rollers. Here's some ball bearings. All kinds of good stuff there. And you should go to, and in fact, we might do this. You can go to McMastercar.com or Grainger or MSC or any of these industrial suppliers and look through their bearing selection. It's astonishing. So the simplest bearing is called a journaled bearing. And in this case, you've got a shaft that goes through the bearing, which is some softer material, say a brass or bronze or something like that. And it just rides in there. That's the entire bearing. And it's lubricated as it starts rotating. When it gets to the correct speed, it actually becomes fully hydrodynamic, and the parts aren't actually touching each other. I did not bring, but if you have an old hard drive and you pull the top off the hard drive and get the spinning platters, you can make an electrical connection between the base of the hard drive and the top of those spinning platters. And when the hard drive is stationary, there's an electrical circuit there. But as you start spinning it, and the lubricant starts getting spread around that bearing in there, the electrical connection actually goes completely away because there is no mechanical contact between those 2 parts. It is a lubricant interface all the way around. It's completely hydrodynamic. So there's no wear, virtually, on that surface. It'll last forever, or for 5 years. That's the average life of a hard drive. But you can have these plain old drilled through ones. You can have them with a flange on them. They come in all kinds of ways. You can mount them in pillow blocks. And they're really good for, if you look at the table in an engineering book, they're going to tell you that it's good for very low to very high speed applications, which is horribly not useful and non-descriptive. Generally, you would use these for lower speed applications. They can be used in high speed applications, but you really have to know what you're doing, which I don't. So I use journal bearings for low speed, high load applications, generally.
Go ahead, it's pretty fast.
Yeah, so like I said, you can use them in high speed, but you have to know exactly what you're doing because hard drives are 7,200 RPM, generally. Excuse me. You use them every day. This is, how many of you know the basics of like how your internal combustion engine in your car works? Like what the parts are?
I watched multiple videos about this.
Okay, yeah. So a few people. This is the crankshaft, which is where all of your pistons mount. And these spaces where the bearings are called the journals. And so you often hear people that are grinding the journals or redoing the journals if they have some damage to their engine. And you've got the piston, and it's connected with this connecting rod down here, and here's the actual bearing. So journal bearings let the pistons move around the crankshaft. Very low friction and very low wear. You know, your car lasts for 100,000 miles at thousands of RPM, right? Roller bearings are really nice for any speed application, really. I've got a few, I'm going to send some around here. Let's see. Start one up here. Send that back to Ben and start it. You should grab a set of these, and I like to use these for laboratory equipment stuff. They're skateboard bearings. They're mass-produced, they're really cheap, and they're good for pretty decent RPMs and loads. I think this entire container of 10 of them was like $12 on Amazon, and it was Prime. So they're really nice to have. The idea is you mount this in some kind of fixed housing, and on the skateboard it's the wheel actually. And then you've got an axle that goes through, and if you grab very carefully just the center part and spin it, you'll feel it's actually really low friction. And this will run for a really long time and be just fine supporting that shaft. And you can, like I said, you can get them in any size, but it's easier to get a common size, and skateboard bearings are the most common size around. So if you look inside this, these have a side shield on them to protect dust and grime and dirt from getting in because they go on skateboards. But you would see all of these little hardened steel balls with a separator that holds them fixed apart. That's called the cage, and it rotates. These are called REMs, rolling element bearings, if you're looking them up in a catalog, because they don't have to be ball bearings. They could be cylindrical. They could be these really long, narrow cylinders called needle bearings a lot of times. So pretty wide variety out there. And here's the cutaway version of that. So you've got the outer ring, which is what you're holding on to when you grab it. And you've got the inner ring, the balls in the cage, which you can see kind of part of the cage is that split material coming out the side. You'll also hear the inner and outer rings referred to as the bearing races. That's another term that you'll commonly hear is people say that the races of the bearing are worn. It just means that those are worn out and the bearing needs to be replaced. And they're used in tons of stuff. Little electric motors, computer fans have ball bearings now. Everything has ball bearings, and the common application would be on some kind of rotating shaft, right? The thrust bearings are a little bit different variety. I've got one of these too, and don't worry about spilling. Unless you push really hard, the balls are going to stay in the cage, so you don't have to worry about dumping them all over the floor, unlike some bearings. Thrust bearings are used for axial loads. So those skateboard bearings are for radial loads, right? You've got a wheel that's pushing radially on the axle that's holding it. Or you've got a rod that's being twisted and there's radial force on the bearing. But what if you've got, this is a rod with a shoulder that's pushing against, let's say this is a casting or some part of your frame. You need a bearing there to reduce the friction so these two surfaces aren't rubbing on each other. So that axial load is what you use a thrust bearing for. The most common thrust bearing that you might be familiar with is a Lazy Susan, in the middle of your table. That's a thrust bearing. It's got an axial load on it. So you can take this, you can actually pull it apart and see the races. This is a cheap bearing, so the races are actually not that great. But again, you can get these on Amazon for a few bucks and they'll serve you just fine. Linear bearings are really useful for a lot of things. And they are bearings that work in one dimension, so you are constraining your system not quite just to 1 degree of freedom, because as this sits, it would also rotate around the shaft. You would have to fix it somehow. But the idea is you have a rod of a common diameter, 10 millimeters, 15 millimeters, those are kind of common linear bearings you can find. And this gives you a very smooth sliding surface to go along. A common application of this, and this is a DIY version of it, so you could build this for about 60 bucks, is a camera trolley. So you see people that have those time-lapse videos, say of stars or something being built, and the camera is slowly moving. This is what they're using. They have the camera mounted on, in this case, 4 linear bearings along these 2 rods. So now it's constrained to only 1 degree of freedom, because it can't twist or can't do anything like that. It can just move in this direction. And they've got a motor down here with a long belt that very slowly pulls the camera along those linear bearings. You can also use, let's see, we've got it over here. This isn't really a linear bearing. This is a kind of roller bearing, really. But Chris used this in the lab to have a linear translation with bearings on it. Do you want to say any more about that, or?
That was a commercial product
Yeah.
a while ago. Yeah, a bunch of needles in those pressure force. It was, I think, designed to handle about 125 kilonewtons.
Right.
So we used it to turn the double direct shear configuration into a single direct shear, still transmit the load, not, in theory, it's more or less friction.
Right. So it's sort of a linear bearing, but not really. It's also what you do when you're moving heavy pieces of equipment or something. You might put steel pipes under it and roll the equipment along the steel pipes to make it easier to move. Same idea. One thing that you do need to consider is all bearings have a little bit of play in them, meaning that there's some wiggle room, a little bit of unconstrained motion. You can remove that by preloading the bearings. There's a lot of ways to do this. We're not really going to go into it, but a common example would be on your bicycle where you've got the crank, where your feet go. There are two bearings in that assembly, and they are preloaded so you don't have significant wobble back and forth. And you can do preloading a couple of ways. Here they're showing you pushing the bearing down onto some shims with this plate that's bolted down. Another way, and kind of an easy way sort of, is with springs. You've got springs that are pushing on the bearing to take the play out. That's really great because, say, if your part's going to experience significant thermal expansion and contraction, those springs can help take up a little bit of that. Whereas maybe the cheaper way is by using a solid preloading device. So here we've got the bearings, and then we've got these nuts that are screwing in on this threaded rod to push on it and preloading the bearing so that play is gone. All right. Springs, I've got one entire slide on springs because everybody has played with them. But don't forget that they exist when you're doing your designs, because sometimes you're like, oh, I need something to pull this, and you come up with some complex thing when a spring would have done just fine, and it's 39 cents from McMaster. There are torsional springs like this, where you can twist, and they resist that. Tensional springs and compressional springs, and every possible variety that you can think of. If you go online, which again we'll do in a second, you can get all kinds of different ratings of springs, from tiny things to springs that support train cars. You can also make your own. You can get this spring wire and wind your own springs on a lathe if you can't find a spring that exactly suits what you need. Okay, so flexures are a really nice way to constrain movement. And I'm going to show you a video on this in just a second. Actually, we're going to watch like 4 or 5 minutes of this video, see how the time's going. But a flexure is you have these bendable elements. So here we've got 2 plates and 2 bendable elements that are, let's say, riveted in between there. And so if you push on the top plate, those are going to bend, and it's going to translate in one direction only. So we're constraining it to 1 degree of freedom. There is some error with this kind of flexure design, though, because as we push it and as those bend, we're actually going to go down slightly, right? So you have to decide if you can tolerate that error. But these are really nice, and they're super reliable because there are effectively no moving parts in the sense that nothing is sliding past each other, right? It's just bending of the element. This would be an example of a one-dimensional flexure. So we've got a couple of plates with all these little leaf springs. This is some of that spring material I said you could buy, but it's flat stock instead of round. And so as you push on this center part, it translates in one direction only. It can't go side to side. It can't twist. It can't do anything like that. It's very well constrained. Another thing that you should note, this is Nitino. This is the material that these spring strips are made out of. It's very hard to spot weld or do anything with, really. So you clamp it between a couple pieces of material that you can weld, say stainless steel or steel, and then you weld that. Notice how they have these bends here, and that is to reduce any stress concentration as you're moving the flexure. Make sure you consider where stress concentrations could be if you're designing a flexure. We're going to try audio again here. I think that we figured out a way to do the sound control. This is a video from, there's an 18-part series that this person made. His name's Daniel Bart. He's a very, very good scientific instrument designer. We're not going to watch the whole thing, but he talks about milling, he talks about different materials he can use, talks about lathe work, all this stuff. And in this section, he talks about flexures, and he shows you a few flexures and how precise they can be. Maybe. Let's reload him.
So what we are going to cover now is flexures, because especially if you have a water jet and if you work with sheet metal, it's very, very easy to make flexures. So I will describe a few types. The classic flexure is simply a big block cut out where you can put in not just one stage, this is the linear stage, which I'll explain later, but you can also put reduction levers in order to get any kind of range you want. So if you carefully follow Harmonic Gearing, the first stage is a 5-to-1 reduction lever, where this is a pivot. This end is a pivot. This piece is called a wiggle bar. It's used to eliminate the effect of to eliminate the fact that this is actually rotating around the pivot. What you want is you want a straight line motion. So you have to put in a bar that the effect this rotates wouldn't be transferred to the next stage. Okay, it's basically decoupled the linear motion from the rotation. So these wiggle bars are like standard when you have multi-stage flexures. So you have here a lever with a micrometer screw, a wiggle bar, and an identical lever. This for identical design, the pivot is on this side, and there's a wiggle bar again. So this is a 5-to-1, it's 3-to-1, so you get a 15-to-1 reduction, coupled to a classical design linear motion flexure stage. So all this is cut out for one piece on the water jet. If you want a very high accuracy flexure, you really should pre-drill the holes, because how well this moves and how linear it is, how much it follows a straight line, depends on the exact matching of all the pivot points or the elastic pivots. Now the water jet isn't accurate enough to give you a straightness of gravel, say in the range of 1 micron. So what you have to do is to drill and read these holes, then make all the other cuts to the water jet. Align the water jet to one of the holes and add all the cuts. Now this way you're going to get, say, a range here, which is maybe 2 millimeters travel, following a straight line to 1 micron. Now for example, if you look at the meter here, it's hooked up to a capacitance gauge, which measures the position of the linear stage, and the meter is set at the highest gain here, which is 10 nanometers per division. So you can see there's no problem moving it 10 nanometers at a time without any backlash. You can go forward and backward without any backlash and easily set it to 10 nanometers. Now this flexure is just a tutorial, so it's made of aluminum. Obviously aluminum is very temperature sensitive, about 22 and 6 ppm per degree, so even you can't have aluminum if you want the stability. So in real life this will have to be cut out with invar or maybe some glass like wool or some other material that is very stable with temperature. You can see because it's made of aluminum, if I put it somewhere and I just put my hand over it without touching it, it just drifts from the radiated heat from my hand. So it drifts at like 100 nanometers just from the radiated heat. I take my hand away, so it drifts slowly back. So it's slower one way or the other. So obviously this is not designed for this kind of stability, but the principle, the layout is classic flexure. You can make those at any size, of course. Now this is an example I showed earlier. This is a bit, that's about as small as you can make on a a water jet? Because here,
So he's got 10 nanometers control on linear motion of that stage, and it's straight to 1 micron over a range of 2 millimeters. So that's pretty incredible control and constraint of motion by using these flexures that are cut out of one solid piece. This, I mean, we won't go on, but you should definitely go watch some more of his videos or watch the rest of this one. But this is actually a 3-axis positioner that's cut out of a material that's very low thermal expansion coefficient. And he talked about MVAR, which is one material that if you need anything that's not very thermally dependent, you should cut it out of MVAR. It's a metal with very, very low thermal expansion. It's also very expensive and very hard to machine, so make sure that's really what you need before you do it. Okay, so any questions on flexures? No? All right, we're actually going to go to the internet once again. Somebody put a lot of time into the Wikipedia page on gears and made really nice animations, better than I can make. I'm going to pass around a couple of gears. These are actually 3D printed, and they're used in my 3D printer. They've worked for a very long time. These are herringbone gears. They've got these chevron-shaped teeth, and they mesh very nicely. They're used in this case for reduction. So the motor turns here, and it moves this big gear a very little amount to precisely control the positioning on the 3D printer. But I'll send those around. This is the kind of resolution you can get out of a 3D printer if you really tweak it, and it's pretty amazing. So they're the regular gears that everybody's probably used to seeing. There are all these bevel gears you see commonly in like car transmissions. This is a common assembly. I'll go down to the animation here. In equipment, worm gears. So this could be attached to a shaft that either a motor's turning or that you're turning with a knob. And for many turns of the worm gear is one turn of this big gear. So it's a way to do reduction generally and also change the axis of motion. There are all kinds of weird non-circular gears that you could play with. Rack and pinion is a very useful setup as well, where you've got this sort of a linear gear with teeth and then a rotating gear. That's how steering in cars did, probably still works, I'm not sure, where you would turn this and do linear translation on that axis. There's all kinds of crazy sun and planet gears and planetary gear configurations that we won't go into. Harmonic gearing is another fun one that is used in some deformation apparatus, actually, but you should go read the page on harmonic drives. We're not going to go into them here, but they're pretty fascinating. It's a flexible inner gear driven by this elliptical cam there. Anyway, and they've got all this stuff on Wikipedia, so go check it out before you do anything with gears. But we're not going to go over all the types, or we would be here for a long time. Another way you can transmit power is by using chains and sprockets, like on a bicycle, except these come in all sizes. There are some tractors and trucks, like large heavy trucks, that have chain drive, and except the chain links are this wide and like this big. I don't know that would be really commonly used in a lot of laboratory gear, except for maybe high torque, a motor moving something or translating something. But belts, on the other hand, are, I would say, relatively common. You can have V-belts, a V-shaped belt that rides and grooves on a pulley, like is shown here. There are several of them teamed up on this motor driving whatever this piece of equipment is, so that it has more torque capability without the belt slipping. But one of the things I think is most useful are these notched belts, kind of like timing belts. So you have these pulleys or cogs that have teeth on them that mesh with the teeth molded into the belt, and you can do very precise positioning with this, or relatively precise positioning. I'm not going to say very precise after we just saw the Flexure video. But now this is how 3D printers are positioned. This is how the print head in your printer scans back and forth. That's how scanners move the scanning bar, all that stuff. So if you need these belts and pulleys, you can generally salvage them out of printers pretty easily. And does that make sense to everybody? These used to be thought of as for relatively low torque applications, but there are motorcycles now that are belt driven instead of chain driven. So there's some pretty strong belts out there. All right, so for the last section, I want to talk about prototyping materials and lab materials, because you need to start thinking about what you're going to build your project out of. And I'm going to show you some common materials, how they're used, and these principles of mechanical design that we just talked about. First thing is you have to have a lot of hardware on hand. We have a lot of this hardware up in the lab. And this would be, so we got 256 metric, 4, 6, 8, and 10 size screws. Those are probably the common things that you're going to use for your projects. I don't see anybody that would need, huge bolts or really, really tiny things. And it has to be organized. This is more for if you have your own setup at some point. This is Adam Savage from Mythbusters. He has an excellent video on his website about, he uses these containers called Sortimo to organize. Unfortunately, they're very, very expensive. So you can make your own. You can order these on Amazon for about $10 each and make your own Sortimo thing. You can put even down to number 2 screws and nuts and washers and everything in little compartments, and then pull it off the rack and carry it like a briefcase, and they don't mix together. It's the best $10 you'll ever spend after you have to sort out tons and tons of little parts when you drop something. And you can also use bins and all this. Up in the lab, we have 2 big cabinets, and then we also have drawers under the workbench that have all kinds of stuff in it. I'm not going to say that they're quite that organized, but yeah, Chris is shaking his head no. But we've got a lot of parts. So before, go ahead and specify that you might need number 4 screws, yada, yada, but we'll check and we might have them, so we don't have to order them for you. Another thing that I would encourage you to do as you're doing your design is to make tons of what are called paper prototypes. These are not just toys. They're actually really useful design tools. You can print out on a 1-to-1 scale your design in Onshape, glue it to a piece of cardboard, cut it out, test fit things together, make sure that's what you want before you actually have the parts machined and cut. It could be something as simple as here somebody was mocking up a car dashboard. You can see there's turn signals, parking, low fuel, a little screen for the odometer and everything, and then 2 needles, probably a tachometer and a speedometer. So that's really simple. It's an Amazon box. So safe cardboard, it's handy. This, on the other hand, is a little bit fancier of a paper prototype, right? But you can see inside they have the drawings glued on from where they cut things out. And this was done by a professional organization, and it turned into a product. So that is how they started mocking out this product, because it's very expensive to get all of these plastic molds made. You need to know exactly what you want. So it's a Dyson vacuum. If you go through the hardware store, you'll see there's lots of great materials to build your project out of. Though I like building everything out of metal, it is expensive, and the tooling is expensive, and it's expensive to work with. Wood is actually a pretty great material for a lot of things. So plywood, MDF, which is it's multi-density fiberboard or something like that. I don't remember exactly what it stands for. OSB, which is oriented strand board. These are all kind of cheap at the hardware store, and big 4-foot by 8-foot sheets. So you go buy a big 4x8 sheet and get a saw and cut it up and make whatever you want out of it. You can make a frame, a front panel, whatever. There's this link in the slides, Hackaday, Materials to Know, that goes over a lot of materials like plywood, like MDF, and tells you things you should know. Like, for example, an MDF, which is it's probably what these tables are made out of. Actually, it's when you buy IKEA furniture and it's glued together sawdust, basically. You don't want to just put a screw in it because those threads will not hold. It'll just pull out. So you want to go ahead and use a bolt, some nice big washers to distribute the load. Have all kinds of helpful tips like that on that website for all of these materials. So it's handy to go and look at. Plastics are a good choice. Acrylic, which is plexiglass, is clear. Delrin is a good one. Polystyrene is super easy to machine. PVC. There's tons of different plastics out there. There's some that have properties like anti-static, everything else. You can buy them in sheets and rods and whatever you need. And it's pretty easy with a heat gun to actually form these plastics around some kind of mold or something that you want. So you can make these nice curved panels or enclosures. Metal comes in all kinds of varieties. We don't really have a metal stock in the lab. The machine shop has a metal stock. You can go to Home Depot and they have very limited metal stock. There are metal supply yards around here that have everything you could possibly want. But you should look up and see, because there's a very good chance if you're thinking, oh, I need to have these two plates and bolt them together in some way where they're at right angles, or you could probably just use a piece of angle iron that's already made and really cheap. So it's worth looking, seeing what you can get in. You can get angle iron, you can get tubes, you can get U-channels, you can get completely enclosed sections, all kinds of metal out there. Plastic tubing, which we do have a lot of in the lab, is wonderful for many, many things other than just putting fluid from point A to point B. One of my favorite uses for this that a few of you might need for your project is, say you've got a motor, one of your, maybe a little motor out of your kit, and then you have some other thing over here that you want to drive. You take a piece of plastic tube and you put it between them and use two little clamps on the end. And it's a very good coupler that tolerates a little bit of misalignment and helps reduce the vibration. You don't have these two things rigidly coupled. So plastic tubing can be used for all kinds of other reasons. And there's a wide selection of it. This is some random hardware store that I found a picture of on the internet. But this stuff's cheap. It's a few cents or tens of cents per foot. So it doesn't hurt if you're in the store, buy a couple feet of everything that you think you might need for your project. And then, of course, a variety of tapes and glues. I'm going to talk about adhesives a little bit next week. We have a lot of these around, but there's all kinds of double stick tape, anti-static tape, special purpose epoxies and glues that you can use in your project to maybe eliminate the need to, say, do some welding or something that could be an expensive process. This is the PVC part that I was talking about. The plumbing section at the hardware store is your friend when you're prototyping things. So this is one that I found online. This is something that I've built, but PVC makes really cheap ways to make frames to do things. You can get all these different fittings and elbows and T's. The pipe you can buy in a 10-foot long section for a few bucks. It's easy to cut. You can cut it with a hacksaw. And then you can glue it and make watertight permanent assemblies. So it's a really handy prototyping tool. Make sure that you're using either drill bits that are specifically for plastic or that you have it well clamped. Otherwise, you can hurt yourself pretty bad when you're trying to drill it. T-slot is another one that you should keep in mind. This is a product called MakerBeam. So it's, I think, a centimeter wide or something. It's pretty small. But if you look end on at one of these black pieces of metal, so you've got a square, but in each side, which I can't draw very well, there is a T-shaped slot that you can put a bolt down in or one of their special fittings, and you have this sliding joint that once you tighten it, things are very firmly secured together. This is great for making little frames like this, for making test stands, for making anything that needs to be fixed or adjustable, movable. It's fantastic. There's a bigger product. So MakerBeam is the small one. I think they even have MicroBeam, which is smaller. I've never found a use for that, though. 8020 is the company, so 8020.net, that makes the bigger stuff. They make things from just a little bit bigger than MakerBeam to things like this. And they've got it all in stock, generally, and all kinds of fittings. It's used in laboratories a lot to make these test stands. It's used in industrial settings quite a bit because it's much cheaper than having this entire thing welded up, and it's much more versatile. We use it too. You may not recognize it, or you might if you've been around the lab, but this is the end of the biax, and back here it's all the hydraulics, all the servo valves, and then the front panel mounted here. All of this is 8020 material. So that entire frame was built out of that and all the support structures. This is MakerBeam. So this is smaller. It's mounting a DC-DT, or a displacement transducer, on this block. And it's hard to see because everything in the image is black and we're on a bad projector. But if you loosen these nuts, then this entire assembly can slide in the T-slot, so you can position it, and then you tighten them back down and it's fixed again. So it's handy for making adjustable things. Likewise here, you can loosen this and slide that up and down and then tighten it. And this stuff is relatively cheap. I mean, you can buy a 3-foot stick of the maker beam for, I don't know, it's probably $15 or so. It's not bad. Actobotics is one that you should definitely look at because they make these parts by the thousands or maybe more, so they're much cheaper than if you were to design this and have it sent off to the machine shop. You can get them all at SparkFun. There's probably other places that sell them too, but I know SparkFun does. I'll show you some of what's out there because I think it could be very useful for your projects. They have all kinds of mountings, bearing holders, hubs, things to attach wheels to motors, some kind of motor attachment. Here's a clamp. So all that is out of aluminum. It's relatively cheap. They've got structural pieces. If you want to build your frame, they've got these U-channels, and they've got angle brackets, round mounting plates, hundreds and hundreds of things for building frames. They've got tons of pretty much every kind of gear. Those timing belt pulleys, they have those. I don't think they have regular V-groove pulleys. And then they have the metal shafts and tubes as well, which you can order from McMaster or an industrial supplier. But if you just need a short piece, McMaster is going to make you buy a long piece probably. You can just buy it from there. And of course these are the rigid couplers, which I said I like to use a piece of flexible pipe if I can, instead of using rigid couplers to couple two things together. They also sell motors and switches and all that mount directly into their mounts. So you can build a pretty complicated robot out of just their parts. Wheels and servo mounts. These are things that you could cut out on the water jet, but by the time you design this in the CAD tool and send it to Ellis, and the shop rate is $60 an hour, and he puts the aluminum plate on the water jet and cuts it out, you could probably buy 10 of these. So if you can make something that's already made work, do it. And places you can look to buy things. These slides aren't up quite yet, but they will be hopefully this afternoon. Of course, the local hardware store is a good place to go. Amazon, a surprising amount of hardware is on Amazon, and most of it's Prime, so you can have it in 2 days for free shipping if you have Amazon Prime. McMaster Car, Grainger, these are both industrial suppliers. Also MSC, which I'll put on here, is another industrial supplier. For metal, sidecuts.com. This is where a metal yard gets a huge piece of metal, a huge plate of metal, or a very long rod, and a customer maybe didn't order that exact size. The customer buys the sheet, and the metal yard trims it for them. These are the trimmings. So sometimes you get trimmings that are 6 inches wide, and that's perfect for what you need because you need something that's 2 by 2. So you can buy this really cheap, below the market price on side cuts. And they have all kinds of material. It's worth looking at. Tap Plastics has every imaginable form of aluminum, or not aluminum, sorry, of acrylic bar sheet, mirrored sheets, all that kind of stuff. And they're in California. They ship pretty quickly, though. eBay, you can get a lot of cheap materials on eBay, or people's side cuts or end cuts. Sometimes machine shops will put their end cuts on eBay. And for electronics, of course, SparkFront, Adafruit, and Pololu are good websites to go to. I'm going to put a page on our course website that has links to a lot of these, but it'll probably be next week when it's up. So things you should do, we're going to have an activity for the last 10 minutes here, but things you should think about doing is pick a random night. Tomorrow's Friday night. You probably have nothing better to do on Friday night, but go walk through the hardware store. It is wonderful to do this because the hardware store generally looks something like this, or it's Home Depot and even bigger. And you don't know what's there until you go and just walk up and down the aisles and look at everything. And you're probably thinking, I don't need a pipe hanger for copper pipe. And no, you don't. But you might need something to support a shaft in your design at some point, and that might be just what you need. It's pre-made and it's $2 on the shelf. You don't have to design it and have it cut out at the machine shop. So go walk up and down the aisles and don't pay attention to what things are, just pay attention to what they could do. So look at how they're made. Look at how things around you are made, so products that you're using or liking. Think about how they were done, what's holding them together. Start hoarding parts now. So if you find something that is junk, if you find a printer at the end of the hallway that somebody's throwing out, take it home and pull it apart because there's at least 2 stepper motors in there. There's a bunch of gears. There's some springs. There's a really nice rod and linear bearing. So salvage all that stuff. And I've got a huge box in my closet that's salvage parts like that. And you never know when you need it. In fact, when Carrie and I were building a demo for the lab, we dug into the junk box and found exactly what we needed, didn't have to order, didn't have to wait, didn't have to spend any money. You can go online to like McMaster, MSC, and Granger and request a catalog. This is the McMaster catalog. It is over 7 pounds of paper. It's huge. And if you flip through that, have the TV on some night and just flip through that catalog, and you will find things you didn't even know existed. And again, you'll be able to use them. And there's a lot of blogs online where you see people talking about new parts or using parts. Of course, the McMaster website, the Granger website, they're wonderful if you know what you're looking for. It's not necessarily easy to browse. Getting a catalog, there's no replacement for just sitting there and paging through it.
Still, I haven't gotten the master catalog in a while. It's still pretty easy to get one from them.
Yep, you go to their website and request a catalog. It might not be super fast, but we have a McMaster catalog. Actually, have more than one if you want to borrow one and go look through it.
McMaster catalog is just absolutely amazing to flip through. It's almost as good as walking through our brick store.
Yeah, and they have beautiful drawings and renderings of what stuff looks like.
How does it work?
Yeah. So, and then you can go to their website and download the CAD model, import it into Onshape, and put it right into your design. It's beautiful.
They're super fast at delivering stuff too.
If you order by 5 p.m. today, it will be here tomorrow by 8 p.m. And that's without paying overnight shipping. That's UPS ground, because their warehouse is in Ohio. So it's great. You don't have to pay the price. It's faster than Amazon. And the shipping is not bad. I think their shipping minimum's $11, but it's not too bad. And that's, I've had McMaster ship a 6-inch in diameter, 6-inch long, solid chunk of 6061 aluminum, and it was $11. And they shipped it all the way across the country. So it's a great place. The activity for the last 5 minutes here is go to some of these websites. So I will pull up McMaster right now and give you a taste of what's there. McMaster.com. And you can see here's all there's screws, washers, shims. You can go down here. Let's see, I may have already passed it. No. Gears, motors, bearings, pulleys. There's linear bearings under linear motion. Some drive shafts that we didn't talk about. Electrical, raw materials, here we go. So you can go to raw materials, metal, let's say. You can see I've been here a lot before. Let's say I'm building a front panel for something and I need a steel sheet and maybe make it out of 6061 aluminum. And here's all the 6061 aluminum they've got. You can filter it down by size and all kinds of stuff. So look through here, make a list of stuff that you think you're going to need for your project. Ideally, by next Thursday, you'll have a list to us of things that we need to order for you. So it doesn't have to be everything for your project, but hopefully most things. So start making that list and bring it to us or email it to us by next Thursday. All right? Okay, we got about 5 minutes.